Okay, welcome everyone, and I'm really happy to introduce today's speaker, Katrin Meusburger, and Turaev-Viro State sum models with defects. Please, Katrin.
Thank you very much for the invitation and also for the nice introduction. I'm going to talk about Turaev-Viro State sum models with defects. Since I'm not so sure what is the background of everyone, I'll start with a little bit of motivation. Then I'll just explain the standard Turaev-Viro invariants. And then in the second part of my talk, I'll explain how we include the defects there. And if something is not clear, please feel free to interrupt at any time and just ask. Okay, so first a little bit about the motivation. So what is a Turaev-Viro or Barrett-Westbury invariant? It takes the algebraic data a spherical fusion category. So this was originally formulated by Turaev and Viro for a specific case, and the spherical fusion category formulation is due to Barrett and Westbury. So one needs this algebraic data, a spherical fusion category. I'll explain what this is later on. And what one gets is an assignment of a number, a complex number, to every closed-oriented triangulated three-manifold. So you take a triangulated three-manifold, you label it with data from the spherical fusion category, and in the end you get a number. This can be also extended to oriented compact triangulated three-manifolds with a non-trivial boundary. And in this case, one gets a linear map from some vector space that is associated to the boundary to the complex numbers. And the nice thing about this construction is that it gives a topological invariant. So in the case where we do not have a boundary and we just get a number, the statement is that this number is independent of the choice of the triangulation. In the case where one has a boundary, this is a little bit more complicated, but what one gets in the end is a topological quantum field theory. And this is not just some topological quantum field theory of interests for the people that only work on that topic, but it also has physics applications. So one application is in condensed matter physics. There are several models that are used as kind of realistic models for topological quantum computer, such as Kitaev models and Levin-Venn models. And these models, they're quite closely related to Turaev-Viro invariants. So basically, they all work with certain vector spaces that are used for the computation, and the vector spaces they assign to a surface is precisely this vector space that the Turaev-Viro invariant would assign. Then it also has some applications in quantum geometry. So there is so-called spin foam models of quantum geometry or quantum gravity, and they're especially important in three-dimensional quantum gravity or Euclidean three-dimensional quantum gravity. So this is kind of the motivation for me to look at a model. And then the question is, why does one want to include defects, and what are defects? So there's kind of not really a standard definition of defects, but what it means in principle is that you don't just consider a three-dimensional manifold, but you consider a three-dimensional manifold where you have distinguished submanifolds that are also labeled with higher algebraic data. So you take as a data not just the spherical fusion category, but some higher data that belongs to it and label the distinguished submanifolds. So these invariants with defects can be of interest from several perspectives. One is that they give some explicit, or you can hope that they give some explicit and quite simple model for defect TQFT, where you do not have to work with very complicated Bordism categories and where you do not have like some hypothesis in there or complicated presentations of Bordism categories with defects. Then another application is that defects are interesting in condensed matter physics. So there are many works on models with defects in this setting. And another motivation is that one can use this to define observables in 3D quantum geometry. This was explored to some degree, but only for some very specific types of defects that are less general than the ones we want to consider. Okay, so that was the motivation. Now I'll explain a little bit about the Turaev-Viro Westbury invariants. So you take a triangulated oriented manifold in the spherical fusion category and you associate to this a number. In order to explain this, I first have to say what is a spherical fusion category. So I'll summarize this underlying structure, and then later I'll talk about the defects and the construction. So essentially a spherical fusion category is an abelian category. So we have direct sums and we have kernels and we have co-kernels, and it's linear over C. That means the morphisms form vector spaces and the composition of morphisms is bilinear. The simplest example one can think of for a spherical fusion category would be the category of finite dimensional representations for some finite group. There the direct sums are just direct sums of representations. The morphisms are just homomorphisms of representations. And this is clearly an abelian category. Then the spherical fusion category is monoidal. That means we have a tensor product, which is a functor from the category times the category to itself. There's a tensor unit, and there's an associator that allows us to rebracket the tensor products. In the example of the finite dimensional representations of a finite group, the tensor product is just the tensor product of representations. The tensor unit is the trivial representation on the complex numbers where every group element acts trivially. And the associator is just the usual rebracketing of tensor products of vector spaces. And in the following, I'll use, as is common, I'll use some diagrammatic notation. So objects in the category for me are little arrows that point downwards, and the tensor product of objects is just putting the lines next to each other. Morphisms are little dots on the lines labeled with objects. So here we have a morphism from x to x prime, here another one from y to y prime, and here's their tensor product. And the composition of morphisms is downwards, and the trivial morphisms and the tensor unit are not depicted. That's just the usual diagrammatic calculus for a monoidal category. Okay, so in addition to just being a monoidal category, the spherical category needs to be pivotal. Pivotal means that for every object, there's a dual object. So in the diagrammatic calculus, we depict this by an upward pointing arrow labeled by the same letter. And then together with this one has also an evaluation and a co-evaluation morphism. So the evaluation goes from the dual x star tensored with x to the tensor unit. And the co-evaluation goes from the tensor unit. So here there's nothing, then to x times x star. And in the representation category of a finite group, these duals are just the representations on the dual vector spaces. The evaluation map is just the evaluation of a linear form on a vector. And the co-evaluation map is just given by summing over a basis of a vector space and the dual basis. And what one needs also here is the double dual is supposed to be isomorphic to the identity, while in the category of representations, this is just the usual isomorphism between vector spaces and the double dual vector space for finite dimensional vector spaces. And with these structures, one can now state the spherical condition. So using the evaluation map and the co-evaluation map, and also the evaluation and co-evaluation for the dual objects, and given some endomorphism f of some object x, I can build two endomorphisms of the tensor unit, which are called the traces. So I can first go from the tensor unit, then I apply a co-evaluation, then I apply f, and then I apply an evaluation. But this I can also do in the opposite direction. I can apply the co-evaluation for the dual. And these are called the left and right traces, and they're supposed to agree in the spherical category. And in the case where this is just the representation category of a finite group, the left and the right trace do agree, and they're just the trace of some endomorphism of a vector space, like the usual trace. And finally, we ask that this category is finite, semi-finite, and semi-simple. That means we have a finite set of simple objects, and every object is the direct sum of objects in this finite set of simple objects. And here in the representation category of a group, this finite set of simple objects is just a finite set of representatives of simple representations. And every representation can be decomposed as a direct sum of these irreducible representations. So I assume here that G is a finite group and that we work over C. So this is just a Maschke's theorem, that the category is semi-simple. So this is the kind of categorical ingredient. If you're not so familiar with the spherical categories, you can also think of this in terms of group representations or a generalization of group representations. Okay, is there questions so far? There's a question. Why is it called spherical? Well, because this left trace and right trace condition. So if you imagine the diagram drawn on a plane, there's no reason why the left trace should be equal to the right trace. If you imagine this drawn on the surface of the sphere, you can just take this and pass it along the back of the sphere, and then it reappears on the other side. So this is something you would expect for diagrams drawn on a sphere, but not necessarily for diagrams drawn on a plane. Okay. Okay, so now how to construct the Turaev-Viro Barrett-Westbury invariant. This is done via a state sum construction. So we take our triangulated 3-manifold and we label it with algebraic data. So every oriented edge in the triangulation is labeled with a simple object from this finite set of simple objects. The edges are oriented, so I need to say what to do with the reversed edge. The reversed edge is labeled with the dual object, which is also a simple object. Okay, then for each oriented triangle, we have 3 edges. They're labeled already with simple object, and we label this oriented triangle with a morphism from the tensor product of 2 of the object to the 3rd one. So here, basically we have a morphism. So this is the picture for it from A tensor B to C. And this morphism here is just the dual picture to this triangle here. So I draw a dot in the middle of the triangle and I draw edges that are dual to the edges of the triangle, and then I get this morphism here. To the triangle with the opposite orientation, I assign an opposite morphism that switches the start and the target. So this goes from C to A tensor B. And this morphism is given by the other one by using the trace. So the trace gives me an identification of this morphism spaces. This is what the trace is needed for, among other things. Okay, then we have an oriented tetrahedron. So this has 6 oriented edges that are labeled with simple objects. And it has 4 oriented triangles that are labeled with morphisms. So here I call this alpha, that goes from C to A tensor B, that's for this phase. Then beta from A to D tensor F, that's for this one. Then I have gamma from F tensor B to G, that's the bottom one. And then delta from D tensor G to C, that's the back one. Okay, and out of this I can build an endomorphism from the object C to itself. So first I apply alpha and go from C to A tensor B. Then I apply beta tensor the identity morphism and go to D tensor F tensor B. Then I apply gamma, the identity morphism on D tensor gamma, then go to D times G. And then with delta, I go back to C. So I have an endomorphism of C, and I can take the trace of this, which is this kind of loop outside. So this is what one assigns to a tetrahedron. And to the tetrahedron with the opposite orientation, there's another such endomorphism of the tensor unit that is constructed from the dual morphisms. And because the endomorphisms of the tensor unit are isomorphic to C, we can interpret this as a number. So to the 4 morphisms, we associate a complex number. So I can see such a 6J symbol that I associate to an oriented tetrahedron as a linear map from a big morphism space that takes the tensor products of all the morphism spaces in the tetrahedron to C. I can also see this more algebraically if I don't want to think about tetrahedra as the component isomorphism of the component morphisms of the associator on the simple objects. So the associator is a natural isomorphism. That's data of the tensor product. I can evaluate this on the simple objects, and I can use the naturality of the associator to decompose it into something like this. So this information is equivalent to specifying an associator, and it comes from the associator plus semi-simplicity. And what I should also say is that due to the properties of the spherical fusion category, this is independent of any choices that I make here when I consider the tetrahedron and start assigning the objects and the morphisms and so on. So I can kind of reverse the order, the orientation of certain edges. I can decide with which edge I want to start evaluating it. I will always get the same number. Okay. And the state sum associated to the manifold is then constructed in a quite simple way. So I take a labeling of my manifold, then I take a big product of all the 6J symbols associated to the label tetrahedra. Then I take another big product of the so-called dimensions of all the edges, or the objects assigned to the edges. So this dimension is just the trace of the identity morphism. So it belongs to a picture like a circle, and it's sometimes called the quantum dimension. Yes, then I take these big products, I sum over all the assignments of simple objects to edges and also of the morphisms to the triangles. And in the end, I rescale it by an overall factor. And this overall factor is just the dimension of the category to the power number of vertices. And in this way, I can construct a number, and this number is independent of the choice of the triangulation. So topological invariance here means that this number that I construct from the triangulation depends only on the underlying manifold, but not on the choice of the triangulation. How does one see this? Well, different triangulations of a given topological 3-manifold or piecewise linear 3-manifold are related by a finite sequence of the so-called Pachner moves. There are two different Pachner moves. One Pachner move, the 2-3 move, takes two tetrahedra that are glued along a triangle and transforms them into 3 tetrahedra that are glued along an edge. So here the triangle is red, and this is removed and then instead glued along an edge in the middle. And the second Pachner move is the so-called 1-4 move. It takes a tetrahedron and subdivides it into 4 smaller tetrahedra by inserting a vertex in the middle and then 4 edges from this vertex. And it turns out that the state sum is invariant under these Pachner moves, and the underlying reason are certain identities satisfied by the 6J symbols. So for the invariance under this 2-3 move, it is the so-called Biedenhahn-Elliott relations for the 6J symbols. But I can also see this as simply the pentagon relation for the associator of the spherical category. So the pentagon relation tells me that the 2 ways of rebracketing a 4-fold tensor product from the left to the right, there are 2 possible ways I can do this with associators, and these 2 ways are equal. And when I insert here in this associator simple objects and use the naturality of the associators, I get precisely the Biedenhahn-Elliott relations. And similarly, one has the invariance of the 1-4 move. This is due to the invariance under the 2-3 move plus the so-called orthogonality relations for the 6J symbols. And these orthogonality relations are nothing but the invertibility of the associator. So the associator is a natural isomorphism. So its component isomorphisms are invertible. And this is basically, the orthogonality relation is just expressed on the simple objects. And altogether, this yields a 3-manifold invariant, something that is triangulation independent, and it extends to manifolds with a boundary and defines a topological quantum field theory. And everything that went in there is just the property it's just the consequence of the properties of the spherical category. So essentially semi-simplicity, traces, and a monoidal structure. Okay, so this is the standard Turaev-Viro and Barrett-Westbury invariant. Now I want to generalize this to defects, unless there are some questions. No questions about this? Okay, then I'll talk about how to generalize it with defects. So the first thing one needs to decide if one wants to generalize this to defects is what is the appropriate algebraic data for the defects. And there are good indications what this algebraic data must be. On one hand, from the context of condensed matter physics, Kitaev and Levin-Venn models, there's a clear picture what the data should be. But also from the more general context of TQFTs, there's some good idea. And what is the appropriate data? So, well, now we have we have a defect manifold. So that means we have not just a manifold, but inside the manifold, we have 2-dimensional submanifolds labeled by something. On the 2-dimensional submanifolds, we have 1-dimensional submanifolds, and on the 1-dimensional ones, we have 0-dimensional ones. The picture is that to the 3-dimensional regions between the defect surfaces, planes, and lines, one assigns spherical fusion categories, but they can differ. They don't need to be the same spherical fusion category. To the defect planes between the regions, one assigns a finite semi-simple bimodule category equipped with a bimodal trace. Okay, so the picture is here. I have a defect plane, and on the 2 sides, there may be 2 different spherical categories, C and D. And to this defect plane, I assign the finite semi-simple bimodule category with the bimodule trace. So what is this? Well, it's a category together with action functors from the spherical categories on the left and the right of the plane times this category M to M. And these action functors can be viewed as some categorification of the notion of a bimodule. So a bimodule is over a ring, well, 2 rings actually, and the multiplication of the rings here is replaced by the tensor product of C and D. So the spherical categories replace the rings, the tensor product replaces the ring multiplication. And these action functors replace the structure morphism of the bimodule. And the bimodule has to satisfy certain conditions. So if I have a bimodule over the ring, it should not matter if I first multiply 2 things together and then act with them, or if I act first with one and then with the second. And similarly, the unit of the ring should act trivially. And here in the category setting, this is encoded in certain natural isomorphisms. So I have one natural isomorphism, which I call little c, that tells me it doesn't matter if I first tensor together 2 objects of C and then act with them on M, or if I act first with one object and then with the other. Only this now is not an identity or equality, but this is a natural isomorphism. There's an analogous natural isomorphism for the action of the other category, D. And then finally, there's a natural isomorphism that tells me that it doesn't matter if I first act with C and then with D, or if I first act with D and then with C. Just as in a bimodule, it doesn't matter with which ring you act first. And then there are 2 more natural isomorphisms that tell me that the unit objects, so in this case the tensor units, that they act trivially. And the only difference with bimodules over a ring is that these are now natural isomorphisms between functors. So they're not strictly identities. So these natural isomorphisms have to satisfy further axioms. And in this case, this is a pentagon axiom that generalizes the pentagon axiom for the associator. And there are several pentagon axioms, one for C, one for D, and one for B, and triangle axioms that generalize the triangle axioms of a monoidal category for these kind of trivial actions. So this is the definition of a bimodule category. Here I also asked that they're equipped with a so-called bimodal trace. So this goes back to Schaumann. A bimodal trace is just a collection of linear maps from the endomorphism space of each object to the complex numbers. So this generalizes the trace in C. And they're supposed to have the usual properties of the trace. So they have cyclic invariance, they must be non-degenerate, and also they need to be compatible with the action of the spherical categories. Okay, so this is the data. What I have to also say is, what do I do if I reverse the orientation of the plane? And in this case, I just take the opposite category with the opposite composition of morphisms, and I make it into a DC bimodule category by taking the opposite actions. So I just apply the duals in the spherical category to the objects and make it this way into a DC bimodule category. And it inherits the traces and all the other properties. Okay, and then finally I ask that all my bimodule categories are semi-simple, so they have a finite set of simple objects, and every object is a direct sum of simple objects. Okay, this looks quite complicated, but in examples it's kind of more reasonable. So the simplest example is a spherical fusion category as a bimodule category over itself. Just as every ring is a bimodule over itself with the left and the right multiplication, every spherical fusion category is a bimodule category over itself with the tensor product as the left and the right action. And in this case, the bimodule trace is just the trace of the spherical category. Another example that is maybe intuitive is one can consider three finite groups, U, G1, and G2, together with the group homomorphisms that embed this group called U into the groups G1 and G2. In this case, I get the statement that the representation category of U is a bimodule category over the representation categories of G1 and G2. The action of these are just given by the action functors are just given by the tensor product of the representations as vector spaces, and then the resulting tensor products are equipped with the induced representation of U. So here the vector space W, and that already comes from U, has a representation of U. The vector space B has a representation of G1, and the vector space X has a representation of G2, and they inherit a representation of U from this group homomorphism. Yeah, and then the trace is the usual vector space trace. Basically, this example is very simple, but one can also do something similar for Hopf algebras. So one could consider, instead of the finite group, one could take a finite dimensional semi-simple Hopf algebra, and then one would not talk about subgroups, but one would consider module algebras and co-module algebras over the Hopf algebras, and one could construct similar examples. And one can, of course, take these examples and make them a bit more complicated. So there's also a possibility of twisting with certain co-cycles and changing a little bit these examples. But for someone who's not familiar with it, this is the simplest example.
Catherine, sorry, there is a question in the chat by Masood. Did you see?
I cannot see it. I'm sorry.
Okay. So Masood, you want to ask?
On mute. Yes, I mean, so I was asking, in terms of Hopf algebras, these bimodule categories, are they like Dieter-Drinfeld kind of modules over the Hopf algebra, or?
So in the case where the category is the representation category over a Hopf algebra, yes, they are bi-co-module algebras.
Ah, okay, so they are simpler than Yetter-Drinfeld.
They are representation categories of bi-comodule algebras, or if one uses duality, which one has in case it's finite dimensional semi-simple,
Okay.
I can also say they are bi-module co-algebras.
Okay, yeah.
And you get them from reconstruction, like in the same way that you can recover the Hopf algebra from the fiber functor, you can recover them from a corresponding fiber functor that is compatible with the action.
Yeah, okay. So they are simpler than Yetter-Drinfeld modules. Okay, thank you, yeah.
On one hand, yes, but we will come to the Yetter-Drinfeld modules soon.
Okay, thanks very much.
Okay, are there more questions? Okay, so if not, then I'll continue. So this was just the higher category data for the defect planes. Now we also have defect lines, and defect lines are labeled with bimodule functors that preserve the traces. So here we have a plane that is labeled by two bimodule categories, M in blue and N in purple, over two spherical categories C and D. And the defect line on this plane, an oriented defect line, is labeled with a bimodule functor from M to N. So this is a functor from M to N, together with natural isomorphisms that tell me it doesn't matter if I first act and then apply the functor, or if I first apply the functor and then act. And I have two of them, one for the action of the category C and one for the action of the category D. And this generalizes kind of the notion of a homomorphisms of bimodules. So it's like a linear map between the different bimodules that kind of commutes with the action, only now it's a functor and not a linear map. These natural isomorphisms, they again satisfy certain axioms. This is a pentagon axioms, certain triangle axioms, and also hexagon axioms. I will not detail this now. And they satisfy compatibility. So the functors we're considering here have to satisfy a compatibility condition with the trace, which is automatically satisfied if it's an endofunctor, and if not, one has to impose it. And examples of this are the following. I can take a spherical category as a bimodule category over itself, and then I can build an endofunctor, an endo-bimodule functor, by just tensoring with an object of the center of this category. And here we are already at the Yetter-Drinfeld modules, because the center of the spherical category is equivalent to the category of Yetter-Drinfeld modules. So Yetter-Drinfeld modules are an example of a bimodule functor. So just tensoring with an object of the center, or equivalently tensoring with the Yetter-Drinfeld module, if I talk about Hopf algebras. Then I can do a similar thing for any bimodule category. I can take a CD bimodule category and an object of the center of C, or equivalently an object of the center of D, and let it act. And in this way, I get a bimodule functor. If I want to think in terms of group representations, what I can do is I can consider a commuting diagram of group homomorphisms. So we have two smaller groups, U and V, which we imagine we embed into groups G1 and G2 via group homomorphisms here. And then we have a group homomorphism from U to V. And this has to be in such a way that these diagrams commute. And then I get a bimodule functor if I just take the induction functor from the representation category V to the representation category of U that is induced by this group homomorphism H. And because this diagram here commutes, this induction functor becomes a bimodule functor over the group representations. So it's compatible with the action of G1 and G2. Okay, but we can think of the center of Yetter-Drinfeld's modules as a specific case of this. Okay, and the last level of structure is the, here I've forgotten to say what to do if I want to reverse the orientation of the line. So if I want to reverse the orientation of the line, I can just take the adjoint functor. So the conditions on the categories and on the functors assure that each of the functors I'm considering here has both the left adjoint and the right adjoint, and the left and the right adjoints are naturally isomorphic. This comes from the traces also. And so I can take just any adjoint of this functor and assign it to the line with the opposite orientation. Okay, and the final layer of structure is for defect points. So we have certain defect planes that are labeled with bimodule categories M, N, and P. Between them, we have lines that represent functors. So here I've just given an example of a trivalent vertex between the lines. There could be other valences as well, but later I'll work with triangles. And to such a point, we assign a bimodule natural transformation from the composite of two of these functors, in this case F composed with G, to the next one, to H. And this is just a natural transformation that is compatible with the bimodule structure. So there's no more data here. And simple examples is, for example, if I take spherical categories as bimodule categories over themselves and some action functors, then any morphism in the center of the category or any morphism of Jeter-Drinfeld modules gives me such a bimodule natural transformation. If I want to work with representations of finite groups instead, I can do things like conjugating by certain, I can conjugate the group homomorphisms by certain group elements, and I can do things like that to make them into bimodule natural transformations. Okay, so this is the data. Now the question is, how do we integrate this data into a kind of geometrical model based on tetrahedra? And the answer is we need to do this by generalizing the 6J symbols. For the spherical category, everything, all the properties of the model were already contained in the 6J symbols. And the 6J symbols, they came from the coherence morphisms of the data. So here for the spherical fusion category, the coherence morphism is the associator for the tensor product. And together with the semi-simplicity, this gives me the 6J symbol. So I label here with simple objects, and I label with morphisms between them, trivalent morphisms between them. I compose this, and in the end, I take the trace. And this information is the 6J, and it's equivalent to the associator. So the idea is, now we have higher data also, and this higher data comes with additional coherence isomorphisms. So the spherical category has the associator, but the CD bimodule category also has coherence isomorphism, namely the one that tells me it doesn't matter if I first take the tensor product and then act, or do it the other way around. Then an analogous one for the category D. And finally, one that tells me that the left and the right action commute. So there are three coherence isomorphisms, and they satisfy pentagon relations. And the idea is now simply to do the same thing for that one does for the spherical category for these coherence isomorphisms here. So I have simple objects in the spherical categories, but also in the bimodule category. And now I play the same game with the simple objects. So here, I'll make this a bit larger. So here I start with a simple object in the category M. Now I take a morphism in the category M that goes from the simple object to K acts on another simple object M. So K is simple also, and it's from the spherical category. So the black ones are from the category C, and the blue ones are from the category M. So instead of tensoring here, I interpret this putting lines next to each other just as an action. So here we have the blue, and on the left of this we have the spherical category, and the data on the left acts on that from the right. So here I take a morphism from N to K acts on M. Then I apply a morphism in the spherical category to go from K to I tensor J. Then I apply one in the category M again to go from J acts on M to P. Then I'm here. And in the end, I go from I acts on P to N. Then I have an endomorphism of this object N, and then I take the trace. So here I use a slightly different notation for the trace because it's a bimodule trace, but this just generalizes the trace of the spherical category. So essentially the only difference here is that some of the tensor products are replaced by action symbols, that my 6J symbol has now two colors, blue for the module categories and black for the spherical categories, and while the trace is replaced by bimodal trace. So this was for the action of C, for this natural isomorphism. I have another one for the action of the category D from the right. Same picture, only now the data from the spherical category is located on the right and it's drawn in gray. And the data of M is still blue. And then I have another one for the isomorphism that relates left and right action. There I get a picture where I have again data from M. This is this kind of blue zigzag in the middle. Then I have one edge where the category D acts and one edge where the category C acts. And again, like I can take the traces, and all of these diagrams just give me complex numbers that are constructed in exactly the same way as for the spherical categories, only that some of the tensor products are replaced by actions. Okay, next step is for the bimodal functor. I can do the same thing because I have two coherence isomorphisms that tell me it doesn't matter if I first apply the functor and then act, or the other way around. Okay, and then I get multicolored 6J symbols. So here we have two categories involved. So we have a blue bimodal category M. This is the data from the blue bimodal category M. Then I have data from the bimodal category N, which is in purple, that sits here. Then I have data from the spherical category C, and the pink data is the functor. So what do I do here? I take some object N in N, then I take a morphism from N. Yeah, here now it looks like a tensor product, but one of them is labeled with a functor. So what does it mean? It means applying the functor. So I go from N to F applied to M. Okay, then I apply a morphism in M that goes from little m to I acts on L. Okay, then I've arrived at F of L. Then I apply a morphism from F of L to P. That's this one here. And in the end, I go from I acts on P back to N, and then I apply a bimodal trace. And there's a similar picture for the action on the right, for the category D, only that we don't have a black edge, but we have a gray edge for D. Yeah, and finally, we can play the same game with the bimodal natural transformation. There's no more coherence data, but the bimodal natural transformation has component morphisms. So what do? Well, we have three different functors, H, F, and G. Then we have component morphisms of the bimodal natural transformations from H of M to Fg of M. And we compose this with the morphisms in the category. So we go from N with some morphism, we go from N to H of M. Then we apply the component morphism here. And then we go from H of M to Fg of M. Then we are here. Then we apply this morphism here in the category that is labeled with the red color that goes from G of M to P. And we apply the functor F to it. And in the end, we go from F of P to N. Then we have again an endomorphism of some object, and we can take the trace. And in this way, one can incorporate all the defect data into 6J symbols in exactly the same way as one has done before, using semi-simplicity and just the coherence data of these higher category structures. Okay. This is the algebraic side of the picture, and now one integrates it into the geometric side. So here we take an oriented triangulated 3-manifold, and the defect data is supposed to live in the dual cell complex. That means we have 2-dimensional defect manifolds and 1-dimensional defect manifolds and points on them. And the defect planes or the two-dimensional stuff, it intersects all the edges of the triangulation transversally in the middle. The defect lines, they intersect the faces in the middle, and the defect points, they're in the interior of a tetrahedron. And we put this data in the dual cell complex. And then in the triangulation, there are different types of tetrahedra. There are some tetrahedra that are just living in the spherical categories. They don't intersect any defect data, so we have just the tetrahedron in the spherical category. And to this tetrahedron, we just give the usual 6J symbol from the spherical category. This encodes the associator for the spherical categories, and its symmetry group is S4, because the orientation of the edges gives me an assignment of numbers from 1 to 4 to the vertices, and reversing the orientation gives me a permutation from 1 to 4. Okay, then a defect plane can intersect the tetrahedron in two ways. Either it intersects the tetrahedron in 3 edges that are incident at a common vertex, or it intersects the tetrahedron in 4 edges. Then there are 2 opposite edges that are not intersected. And to the one that intersects 3 edges of a tetrahedron, we assign like simple objects in the bimodule category to the edges that intersect the bimodule plane. And we assign spherical objects in the spherical category to the remaining edges. For the remaining edges, the orientation is arbitrary, but the edges that intersect the plane, the orientation is non-arbitrary. It's given by the orientation of the plane. So this orientation is fixed. Well, and to this I assign the 6J symbol that is obtained from the coherence data for the action functor. So this is one of the 6J symbols we had before. It has two colors, one for the module category and one for the spherical category. And this is what is assigned to such a tetrahedron. And the residual symmetries are a bit smaller because these edges have fixed orientations. So here we have a residual symmetries of S3. Similarly, for the tetrahedron, where the plane intersects 4 edges and leaves 2 opposite edges alone, we have these edges that do not intersect, labeled by the categories C here and D. And the edges that intersect the plane are labeled by simple objects in the bimodule category. And again, here the orientations are fixed. And for these 2, the orientations are arbitrary. And what we assign to this is the 6J symbol that comes to the coherence data for the bimodule category. So this is the coherence isomorphism that relates the left and the right action, and this is what belongs to such a tetrahedron. Finally, we also have tetrahedra with functors, bimodal functors. There we have 2 bimodal categories that intersect 4 edges. So we have 2 blue edges that intersect the bimodule, the part of the plane labeled M. And we have 2 purple edges that intersect the other part of the plane. And in between we have a functor. And the endpoints of the functor are on 2 faces. Now again, we label the edges that intersect the bimodule categories by the bimodule categories. Orientations are fixed. And the remaining edge in the 2 triangles that have the endpoints of the functor, we label by a functor. And the orientation here is also fixed by the orientation of the functor. Then there's one residual edge that is labeled by data from the category. And to this tetrahedron, we assign the 6J symbol for a bimodal functor. That comes from the coherence isomorphism that tells me it doesn't matter if I first act and then apply the functor or the other way around. The residual symmetries in this case is only a Z2 symmetry. I can reverse the orientation of this edge. And finally, we also have tetrahedra where one has a plane labeled by 3 functors, 3 bimodule categories. We have 3 bimodule functors between them, and in the middle we have a bimodule natural transformation. And such a tetrahedron we assign the 6J symbol for bimodal natural transformation that I've given you before. And here we have no residual symmetries because all the orientations are fixed by the bimodal categories and by the bimodal functors. And now I've used up all the coherence data and I have assigned something to every tetrahedron. And what also follows from the property of the data is that these 6J symbols are invariant under the residual symmetries. So the 6J symbol for the spherical category is invariant under S4. So it does not depend on any arbitrary choices like how do I orient the edges and where do I start evaluating this. And similarly, for the other data, we have residual symmetries. And all of the 6J symbols are invariant under these kind of residual symmetries. Okay, this is like the translation dictionary for tetrahedra in the triangulation into 6J symbols. And then it's clear what to do. One does exactly the same thing as before. One takes the product, one takes a labeling of a triangulation. The labeling now labels certain edges with objects of the spherical categories, simple objects in the spherical categories, and other edges with simple objects in the bimodal categories. Other edges are already labeled by the defect data, namely the functors, but for the categories we label with the simple edges. Then we take the product of all the resulting 6J symbols and of all the dimensions of the objects associated to the edges of the simple objects. This is exactly like before, only that now the edges all live in different categories and the 6J symbols also live in different categories. But this doesn't matter because the 6J symbols are just numbers, I can multiply them. Yeah, then I take a sum over all the labelings with simple objects. And at the beginning here, I put some rescaling factor that is just the dimension of the spherical categories to the power number of vertices in this spherical category. So essentially what was done before, only in different categories. And one can show that this is again independent of any choices that I make on the labeling of the tetrahedra. And these 6J symbols, as before, they just encode the coherence isomorphism of the spherical and the defect data. Okay. Given this philosophy, it's clear now what to do about the topological invariance. Topological invariance means invariance under Pachner moves. So where does it come from in the spherical category? Well, we have two Pachner moves, the 2-3 move and the 1-4 move. In the spherical category, this comes from the pentagon relation for the associator. And the 1-4 move comes from the invertibility of the associator. Now we can do the same thing for the different 6J symbols that come from the other coherence data. All of this coherence data, namely the isomorphisms that tell me it doesn't matter if I first act or tensor, the isomorphisms that relate the left and the right action, the isomorphisms that tell me applying the functor commutes with acting, and also the bimodal compatibility condition of the bimodal natural transformation, they all give me certain pentagons. And these pentagons I can evaluate on the simple objects, and then I get generalized Biedenhahn-Elliott relations that tell me that I have invariance under the 2-3 moves. And similarly, in all of these cases, these coherence isomorphisms here, they are isomorphisms, so they're invertible. And this gives me some orthogonality relations. And this gives me the invariance under the 1-4 move. With this invertibility, I have to be careful with the natural transformations. So the bimodal natural transformations, they have a pentagon, but they have no invertibility. They can be arbitrarily chosen. Okay. So given this data and these results, So this is a kind of cumbersome but straightforward computation where one does exactly the same thing for all these coherence isomorphisms, what one does for the spherical categories. So for the spherical categories, it's in textbooks, and one just stupidly generalizes this to the higher category data. Okay, and if one does this, one gets invariants under Pachner moves that involve also the coherence data. Has this switched in the picture, or is it still the old slide?
It does switch. Yeah.
It has switched. Okay.
Yeah, it has switched.
Yeah. Okay.
Yep.
Sometimes there's a problem.
Yeah.
Okay. And these kind of coherence isomorphisms, so the pentagon and the orthogonality relations, they translate into well, Pachner moves with defect data. Like Pachner moves for tetrahedra that are partially decorated with defect data. So here, for instance, we have tetrahedra that are joined at the side, but they also have like bits of a defect plane sitting in them. And here I have an edge that is behind this defect plane in the middle. So I said it wrong. So the tetrahedra are 3 of them. They're glued along this defect edge in the middle. And here there's also a defect plane. And now I know I can remove this edge here and instead glue the tetrahedra along a triangle. And the defect data is not affected. I can just do this also with tetrahedra that have defect data. And similarly, I can take 2 tetrahedra that are glued along a face and that have a triangle with defect data. I can also insert this new edge in the middle that goes through the defect data. So this is now labeled also with defect data, and it goes through this defect plane. Then there are more of them for all other possible combinations of defect data in the tetrahedra. So I can have 2 tetrahedra glued, one that has a plane that intersects 4 sides and one that intersects 3 sides of this tetrahedron. Here I have data from C, here I have data from D. And I can change this by removing the gluing along this face and kind of glue them instead along an edge. And similarly here's another move where I have some edge behind it, where I can also just remove this edge even if the defect planes are present. Then this continues for tetrahedra labeled with functors and natural transformations. So here I not just have a defect plane, but it also carries a defect functor that belongs to this edge here. And still behind this plane, I can put a new edge and I get the same result. And here the same for this picture, only that now the edge kind of pierces through this kind of defect plane. This is why it's drawn in blue, and it doesn't matter. Of course, it could also go through the purple defect plane, but then it gets too many cases. And similarly with the bimodal natural transformation. So here I have a bimodal natural transformation. And then a functor, then like some defect plane with a functor continues on one side. Here I have a different picture where I have the bimodal natural transformation up here and the other 2 bimodal functors continue. And they all belong to different types of coherence data of this higher category structures. And similarly, I get 4 moves. So I can also subdivide a tetrahedron. So if I have a tetrahedron with a defect plane, I can subdivide it just as before. I can create little bubbles with bimodal data if I want. I can subdivide in such a way that like some of the data pierces through this bimodal plane. I can subdivide in other weird ways. I can also subdivide here if functors are present. I can insert like little bubbles of functors. And I can subdivide if I have a bimodal natural transformation. So in that sense, it does not depend on the choice of the triangulation. It just depends on the defect data and kind of the topological way in which the defect data sits on the plane, but it's still invariant under Pachner moves. Okay, so this was essentially what I wanted to tell you. So in principle, we have constructed a quite simple and explicit state sum model with defects. And we didn't have to make any assumptions on certain categories and so on. I mean, of course, on the defect data, that is unavoidable, but not on the cobordism categories. And And everything that we did was just a very direct generalization of the thing one does for spherical categories. And the principle is just that each tetrahedron gets assigned a generalized 6J symbol. And the coherence isomorphisms of the spherical data and the defect data on the simple objects are encoded in this 6J symbol. So there's no freedom there. That's just something that appears from the semi-simplicity. And the Pachner invariance is encoded in the pentagon relations for the coherence isomorphisms and in the invertibility of the coherence isomorphisms. And this translates into certain relations between 6J symbols that tell me that the model constructed in this way is invariant under Pachner moves. So this gives a rather direct generalization of Turaev-Viro invariance, and it's also quite combinatorial. So in order to see which Pachner moves do I have to consider, I just look at the pentagon equation and I say, okay, how many different ways are there to subdivide this in like groups of 2 and 3 or groups of 3 and 1, 4 and 1. And this is basically, yeah, just combinatorics in principle. Yeah, and one gets this kind of same invariance result as before. And of course, there are many things to do. So one thing I would be interested in doing is to treat concrete examples. Like one concrete example is to consider C as a CC bimodal category and to consider bimodal functors that are objects of the center of this category and bimodal natural transformations that correspond to morphisms of the center. And this is in some way looking at Jeter-Drinfeld modules or isomorphisms of Jeter-Drinfeld modules, if you prefer that for Hopf algebra. And in this case is particularly interesting because some things are already known about this case. So this describes on one hand so-called excitation in all these models of condensed matter physics. In 3D gravity, it describes kind of like point particle things. And kind of particle-like observables or the world lines of such observables. And there are already some results on such models. And it would be nice to see how this more general model fits in with these results and to check how you get these other models as special cases of that. The other thing that would be quite nice to consider is to start with some simple examples that are related to group representations. So in this case, one has some kind of, yeah, simple cases of bimodal functors, bimodal natural transformations. One also has some classification results for the bimodal categories that go back to Ettinghoff, Ostrich, and so on. And one can use this data and the results that they have to treat this case. Then, of course, in the long run, one would also like to extend this to manifolds that have a boundary and to really incorporate this into a TQFT-like formulation. But for this, I think one really needs to understand properly this model first. And yeah, then one at some point wants to use this maybe to get really concrete examples for defect TQFTs and also examples with which one can compute. Because here there's in principle, as soon as you know the 6J symbols, you can compute everything, and it doesn't get much more complicated than for the spherical categories. Yeah, and it's quite concrete, and also basically everything that comes in here that is new can just be incorporated by putting different colors and different letters. And yeah, thank you for your attention.
Thank you, Catherine, for your nice talk. Thank you. Only a virtual applause. Any question or remark?
Yes, I have one general question. And you see, to what extent are these type of developments originating in the work of von Jones on knot invariance? What I have in mind is the following, is that it seems to me that the most natural examples of the type of categories, of bimodule categories that you are considering are coming from 2-1 factors, subfactors, pairs of, you know what I'm saying.
Yes, yes,
So,
and
I mean,
it's also true.
I understood your talk, but what I was missing was, you know, many examples of the type of categories that you were handling. Because so I presume that, okay, then you get invariants for this, you get topological quantum field theory and so on. But I mean, it's important also to describe the other side, which is how you construct examples of categories. I mean, the one that you gave us with a finite group and representations, okay. I mean, but it is still something which is somehow, you know, co-abelian and so on. So I mean, it's a little bit too restrictive.
The problem is in the talk, I've given only one very simple example and one inner categorical example. So the problem is simply it takes a lot of time to write down the examples.
Sure.
But what you're saying is exactly true. And that is also how these categories were constructed.
I see, okay.
So there's work by Müger, for example, and also by Ostrich, Ettinghoff, and they're looking at subfactors.
Yeah, okay.
And there are examples also in textbooks.
Yes.
But even to write down a very simple example just takes a lot of time.
Yeah, of course.
So I wanted to keep it simple because otherwise it just gets very technical. So I'm not saying is that I can very easily compute with the examples from these textbooks.
Yeah.
That is not true. Mm-hmm. One can use them in principle. One could work out with them what it gives, but it's not so simple.
But can you use a computer to do that, or when you have an explicit triangulation of a three manifold? Or?
In principle, yes.
Yeah.
So how should I say? It's already quite, so when you use the spherical categories, it's already quite complicated because you're computing 6J symbols. Mm-hmm. Computing the 6J symbols, even for a finite group, is not so easy. You need more information than just the character theory. And the 6J symbols for a spherical category is also true. But I don't think that it gets much more complicated than that. It just, you have to do it for every example, and it's, I'm not a computer person. I mean, I use computers, but I would not be the person that makes the computation on the computer. But in principle, one could do it.
Yeah, okay, good, very good. Okay.
Very nice. Richard, I think. We cannot hear you, Richard. I mean, you should unmute.
Okay, you can hear me now. Sorry. Let's try to avoid noise. So one thing, so apropos Alan's question, actually. So of course you have this Turaev-Viro invariants which are not independent of orientation. So there are certain cases coming from subfactors where the orientation, when you change orientation, actually the invariant becomes dependent on that.
Yeah.
Right. So it's the question what happens when you reduce down to this bimodal structure. So it's is it correct that when you want to apply it to say take a free manifold, then when you think about its defects, you pick up a submanifold, right? Two-dimensional submanifold.
Yeah.
And then you do triangulations which are kind of consistent with a submanifold.
Yeah.
Right. So if a complement of your submanifold is connected, then your ambient spherical category does not depend on where you are. Right. There's only one.
Yeah. You imagine like something like a sphere that is a bimodal category between two spherical categories.
No. I'm thinking if you say you have a free submanifold. Free manifold, and you have two-dimensional submanifold.
Yeah.
If a complement, it does not have to be, it can have boundary, right? Your submanifold.
Yeah.
Now, if a complement is connected, then your ambient spherical category is just the same. There are not two categories, but only one. Correct, or am I wrong?
So you have only the boundary, and you have a defect plane that hits the boundary.
No. What I have is, say,
or you want defect lines.
Say defect circle in a free sphere.
Okay, but just a circle, not like a circle that lives on a plane that lives in the sphere.
No. So what I mean is if a complement of your defect submanifold is connected, then your ambient category, the ambient spherical category is there's only one. There are no, you don't have two of them, right?
That's at first is not a problem because you can take it you have a bimodal category over C and itself.
Yeah, no, I'm not saying it's a problem. I'm just
Okay.
asking. No, I'm just curious what's happening, right? So in this case, right? So in some sense, you take a pick up. You have your submanifold. You pick up you have your category, ambient category. You have a bimodule. It's a two-category bimodule, right? And then you use this kind of, you reduce, you take triangulation, and then you just do tensor product over this sub-triangulation with your bimodule, something like this, right? It's this kind of reduction.
Like that, yeah. And this kind of tensor product over is kind of implemented by the summing over the simple representation.
Yeah, okay, fine. Yeah. Okay.
Yeah, and this I didn't emphasize, but what you can also have is that you always take kind of just one spherical category, and then you take C as a category over itself, and it's like as if the planes are not there, but you can still have the data on the planes. Yeah.
Yeah, sure.
Yeah.
By the way, if you do that, do you get different invariants?
Different from what?
When you don't have, when you forget, if you forget this plane.
So if you consider only planes that are kind of a spherical category as a bimodal category over itself, then
yes, you don't see it,
different
right?
invariants, and this what you get is essentially there's this work by Turaev-Viro and also by Balsam and Kirillov about the Turaev-Viro invariant and the Reshetikhin Turaev, and then you are only considering the center, and then you get basically this
original invariant, or what?
Yeah, well, I mean, there's a kind of intermediate thing where you can have a Turaev-Viro invariant that is decorated also with objects of the center of the spherical category.
Oh yeah, sure. Yeah,
and
okay,
that's what you're getting.
Yeah,
and
okay.
You can also consider defect planes with only endofunctors, and then you also get something similar because you have a functor that goes from the center of the spherical category to some center of the bimodal category it acts on.
Yeah, okay.
But this I've never worked out in any detail.
Yeah, okay. Okay, because it reminds me very much. So there is this, there is this version of invariance, so Witten's version actually, right? So, or actually Adrian Ocneanu's version. We have a manifold, you have a submanifold, and then you look at, you use your category you pick up a triangulation, and then you use your category to write down state somewhere on the submanifold. You restrict yourself to certain quotient subcategory or certain bimodule category.
Yeah.
And that feels like basically that's what you are doing, right?
It's a special case of what I'm doing. Like what you can do is to take for the bimodule functor, just a functor of the form fixed object of C acts on something. Or you can take for the bimodule functor also something like a functor where the category C acts on a fixed object of M. It's like the
so you pick up a bimodule.
Or also projection are specific examples of functors.
Yeah, okay. Yeah. Okay, fine. Thank you.
Thank you. Any other question or remark? Any?
Jenny?
Jean, please.
Jean.
I don't know this subject at all, so I feel that my question will be completely trivial for you. But among the three manifold, of course, the simplest is the three-sphere. And in the three-sphere, there is a very interesting finite group, which is the icosahedral group that acts in the three-sphere in order to get a regular lattice, okay? Where the lattice is paved by tetrahedron. Let me close the door here, sorry. And there is,
I didn't hear the last thing. You said that there's a lattice and a tetrahedron?
Yes, it has, I don't know what many points. This is the icosahedral group. It's something that is known since Coxeter, okay? And this lattice is regular.
Yeah.
And it's essentially a lattice of tetrahedron. And they are regular tetrahedron, okay? Regularity is due to the symmetry.
How many?
Now, on the three, I think it's 120, but I don't remember. It's
Okay.
120 sites, okay? Anyway, in the three sphere, there is also something interesting. There is a flat torus. And I think that has been used by Kohn and Dubois-Violette to build the quantized spheres, okay? You have a flat torus which describe various interesting foliation, etc. So you have foliation by flat tori. And by flat, I mean, if you embed, if you have these torus and you put the Riemannian structure that is coming from the three sphere, then it's flat, okay?
Okay.
So you could take this flat torus as a defect.
Mm-hmm.
And I just wonder what kind of invariant you have when the category you choose is given by the representation, is given in terms of the representation of the icosahedral group, because as I understand, for each triangle, you have to associate some object.
Mm-hmm.
And I would say that a natural family of objects would be the representation of this icosahedral group. So this is probably the simplest possible manifold in 3 dimensions. So I am curious to see whether this has been studied and whether we know something about that.
So these are like two different things. Like one is to take the specific array of tetrahedra, and the other one is which group representations you take. And they don't need necessarily to be connected. So we haven't looked at this example. And also, like, in order to do this for this icosahedral group, you would need to have all the simple representations and to compute the 6 J symbols for them. And I'm not sure how easy this is.
It's okay. I think this is known. Okay, it's in the book.
Yeah.
I'm not saying that it was easy. It took a long time to get that. The work of Coxeter took a long time. Okay. But it's actually understood and known, okay?
Also the 6 J symbols?
Yeah.
I think so, but I
yeah, all
of
of it is in books, actually, yes.
Okay.
Yes, it's in books.
No, Jean, but I think there's a different problem. So this, which group you pick up has nothing to do with, well, the manifold you are looking at.
I understand, but
right? So these are completely separate things. Doesn't matter which group you pick up in this context, or which category you pick up.
No,
right?
I understand.
There's no relation whatsoever.
I understand, but here this is a specific example.
Yeah.
And I would be curious to see whether this invariant tells you anything that is relevant for something that has been studied so far.
So I suspect it does not. So I suspect if you start taking invariants coming from group representations, you don't get any interesting information. You certainly do not get any interesting information about 3 manifolds. And I don't think it changes anything if you look at submanifolds there. You really need quantum groups or something.
Yeah.
Okay.
So I just gave the group representation as a simple example because I didn't know like how many people will be familiar with spherical categories, and it is an example of a spherical category, but it's not an example of that is kind of very sharp in distinguishing manifolds. Like you could also consider as a spherical category just the vector spaces, finite dimensional vector spaces, and then you would not be able to distinguish any manifolds. So the picture is, like we said, you need to take something that is kind of as complicated as possible, more complicated than a group, but not so complicated that you cannot compute. Yes. But computing with the more complicated examples is not so easy. And there's for example, some computation that looks at length spaces to see if this has more power to distinguish the length spaces than the homologies, and this is worked out, but it's for very simple. So this is already a simple example, and it's not so easy to follow this computation and do it oneself. So I think the group,
But you can deform these groups, that's for sure. I mean, this is a finite group anyhow, so it's possible to deform the
You
group.
think like taking this group representation and then taking a co-cycle and deforming it?
I would suspect that you could get something. And actually, that's the way Alain and Dubois-Violette contest the sphere. Okay, it was a bit simpler, but it was a deformation of the torus I was talking about. So I suspect that it might be an interesting example to look at because everything is more or less explicit.
I think this could be interesting, and I think it could be interesting also if one includes a co-cycle.
Okay. Yes,
or also one could consider the double, the Drenfeld double of the group algebra, which is kind of a bit more has more non-trivial content, and this could be interesting.
Okay.
But we are not so far. So this is work in progress, and what I've said is kind of we are sure, but we haven't treated many examples yet, and it's also quite hard in the pandemic. But yes, I think this could be interesting with the co-cycles, for example.
Thank you.
I have a question. Yes. So, hi, Catherine. Just to understand better, so you're saying that using co-cycles, two co-cycles, therefore leave the category if you started with a symmetric category, you remain in a symmetric category. Nevertheless, the use of a co-cycle could be interesting and give you invariance.
So I think this because they encode information on the associator. So what I had in mind is like this category of G-graded vector spaces. And then basically you have vector spaces that are graded by group G. And in this is kind of a standard example. And there you can think, what is the associator on this category? And then you see you can have freedom in putting the associator. You can either take like one very simple standard thing that you can do, but you can also put a co-cycle. So I was not thinking of kind of Hopf algebra twists by co-cycles, but of putting the co-cycles in that way.
Okay.
And I would think this can be interesting because this is a change of the associator. It's a non-trivial change of the associator that keeps the tensor product intact. And this should manifest in an interesting way in the 6J symbols.
I see. Thank you.
So I don't know if this gives something very nice, but I think it's kind of conceptually interesting if one looks at 6J symbols.
Well, it does give non-trivial invariants. Not difficult ones, but non-trivial. So it does give something interesting.
Yeah. Okay, it depends on where you start finding it interesting. Yeah.
Yeah.
But it's really a manageable example that one should look at.
Okay, thank you. So many questions and remarks. And any more? More questions or remarks? Thank you, Catherine, for the great and for the great reactions. So thank you so much. See you next week, everybody. Stay safe, stay healthy.
Thanks. Bye.
Okay.
Bye.